Okay, let's start talking about the mean value theorem. And the mean value theorem can be, I guess, broken down into two parts. It's a value theorem, meaning that it's going to be some theorem about a value that something can have. And it's also a mean. So mean means average, especially in math. So we're going to think about averages and values, average values. So let's just start with this simple graph. It's going to be a parabola shape. Let's say here to here, something like that, right? And it's going to be defined here to here on this interval, in this closed interval a to b, with the brackets. So we're thinking about average values, and we're thinking about derivatives at the same time. So we're thinking about average slopes or average tangent lines, average rate of change. And I guess the one we want to stick with is average rate of change. The average rate of change for this function from a to b is just the line that connects from a to b, or this line. Let me draw it in a different color so you can see. It's this line. This is the average rate of change. Average rate of change. And notice what it is equal to. It's equal to 0. I would also like to note that this graph, or this parabola, has derivatives everywhere along this value, right? We can find the derivatives here, anywhere we really want to. So I'll say it's differentiable for every value between this open interval. We're not counting the endpoints because you can't find the derivatives at an endpoint. You can only find, I guess, find one-sided derivatives, but you can't find like the real derivative because we have to have that limit definition where it approaches from both sides, but if we don't have one that approaches from the other side, then we can't find the derivative. So I'll say it's differentiable everywhere within those values a to b. I guess this is kind of like a weak version of mean value theorem. This is known as Rolle's theorem. What this says is that if you have this condition right here where the average rate of change is 0 between 2 points, there's going to be a point or a value here where its derivative at a point somewhere here is equal to the average rate of change, which is in this case equal to 0. So there's going to be a point C where its derivative at C is going to be 0. And if derivatives is the slope, what's the slope of 0? It happens here. So that means if we drop this point down, C is going to lie here. So Rolle's theorem just says if you have an average rate of change of 0 between two endpoints, there's going to be guaranteed, as long as it's differentiable within those intervals, there's going to be guaranteed at least one point where the average rate of change is equal to the instantaneous rate of change. But this is not really the full mean value theorem. This is like a weak version. So let's talk about the stronger version, which is the mean value theorem. Basically says for any, I guess, differentiable function, in this interval, in the open interval, here, let me write it a little bit more clear. Defined on the closed interval a to b and differentiable in the open, I guess, the open interval a to b. The average rate of change has this property. There's going to be some value c, so there is a guaranteed c. There's a guaranteed point x equals c such that the derivative of f prime of c, or evaluated f prime evaluated at c, is equal to the average rate of change. So I just wrote it up here, but it's more like this. So what is the average rate of change? Let's kind of go get to a fuller equation of the mean value theorem. I guess that's why I have this space right here. If I have any arbitrary function like this, and it's defined on these endpoints, the average rate of change, if you remember, is just the line connecting those two. And there's a guaranteed point x equals c such that the slope of the tangent line at that point is equal to the average rate of change. And I can see, I think, almost 3 of them. There's one here. There's one here. Kind of blocked by that line, but you get the idea. And then there's one here. There's guaranteed at least one, but in this case there's 3. What is the average rate of change? Well, the average rate of change is the rise over run, or the rise divided by the run. And there's a guaranteed point where the derivative of that point, which could be here, for example, is going to equal the average rate of change. In other words, there's going to be a point where there's going to be an equality of instantaneous rate of change and average rate of change. So we have this definition right here, the mean value theorem. I'll show you it all at once. Let's just talk about how we can make this mean value theorem fail. So how specific it is in this definition, and how we can actually make it fail by changing one of these conditions. So I guess the first obvious case is not differentiable. Let's actually go to not continuous. So this one's pretty obvious. If I have a function defined here and here, and let's say it's defined like this, a piecewise function, notice that there is no guaranteed point that the instantaneous rate of change is equal to the average rate of change. So average rate of change is written in blue. There's no tangent line that has this thing. That's because you can't differentiate it every single value along this. Sorry, here you can't find the derivative right here. And since it's not differentiable along this whole entire interval, it fails, or the mean value theorem does not hold, right? So you can't use that equation at all because mean value theorem fails because it does not satisfy the condition of being continuous. Let's look at one that is not differentiable. The one that's pretty obvious is this value, or this absolute value function. Let's say it looks something like this. The average rate of change is here to here, and it's defined on A and B, right? Notice that because it's not differentiable along this whole entire curve, there's no point that has the same exact slope. You might say here, but because this is a sharp point, we can't find a derivative here. And notice that it never reaches this slope right here, so you cannot use the mean value theorem. So let's look at a couple where they actually hold. So examples of mean value theorem. Mean value theorem. The first example is the sine function. The sine function looks something along the lines of this. And we can pick any points. So I can just take, let's say here, and let's say here. So right here and right here. Notice that this is what we're constricting ourselves to, A to B. And if I draw the average rate of change here, somewhere along this interval, there's going to be that slope, somewhere along this. Because it is continuous and differentiable throughout this entire inner interval, there's going to be a point here. And I can see one graphically, which is right about here. If I were to draw the tangent line, it looks probably something like this, and the average rate of change equals the instantaneous rate of change. Another one could be any polynomial. polynomials are always continuous throughout. So let's look at an example of a polynomial. Let's say it looks pretty crazy. It's something like this. Maybe let me write that a little bit more smoothly. This is just a really wonky polynomial. And let's just define any point. Let's say here, so right here. And let's say, where do we want? We want here, A and B. So B is right here and A is right there. I connect the lines right here. There's guaranteed to be at least one point where this average rate of change equals the instantaneous. So I can see 2 points actually, right about here and then right about here. So if I were to draw the tangent lines or try to sketch it, you can see that the slopes, that's a little bit off, there we go, that's slightly better. The slopes are equal to the average rate of change. So we see 2 examples of them working, and we also see 2 examples of them not working because it's usually not differentiable in between. And then let me just scroll to the mean value theorem and the Rolle's theorem at the same time, because mean value theorem is kind of like a more powerful Rolle's theorem because it applies to any type of rate of change, not just a rate of change of 0. So I would take away mean value theorem, but if you forget what the mean value theorem is, I would look at the Rolle's theorem and see how this can apply to any rate of change, not just 0. So this is just more of a intuition type of video, not really a mathematical or like example heavy. We're just looking at a bunch of graphs and seeing how the mean value theorem works, and hopefully you understand that what kind of conditions it needs to be and how it looks graphically before we do it analytically with actual functions that are defined explicitly. So that's it for this video.